So we're going to pick back up with part 2b here and start with calculating the pH of an acid.
There's 5 different ways to calculate pH depending upon what you're given. So this is very much like what we're doing in the equilibrium chapter. So let's say I want to calculate pH of a strong acid. Because my strong acid completely disassociates, I can just, if I know the initial starting concentration, so let's say if this is 1 molar, then I'm going to produce 1 molar of hydrogen ions and 1 molar of anions. So if I have a strong acid, then I'm going to take my initial starting concentration of the acid and I'm just going to take the log of that. So calculate pH from a strong acid, I can use my initial concentration to directly calculate pH. So if this is 1 molar, then my pH is going to be equal to negative log of 1 molar. And that's going to give me my pH. Let's say I have a scenario where I have 0.10 molar of HCl. Now, this is where remembering that this is a strong acid is going to come in handy because you're not going to have to do any crazy stuff. I also have molar of hydronium ion because it's going to completely disassociate, and that's going to give me a pH equal to 1. I'm going to go out 2 decimal places because I have 2 significant figures here. If I have a weak acid, let's say I have 0.10 molar of a weak acid, say HF. Now that doesn't equal 0.10 molar of H3O plus because this is not going to completely disassociate. So I'm not going to have a pH of 1. So now I can't do this simple math where I just take my initial concentration here and take the log of it and get to that. This is not so simple. So this is going to be more complex because I don't have 100% disassociation. So here is my equation. I have HF, and I'm just going to write water in here because I want to look at hydronium ion concentration. And this just allows me to balance that. And let's say I have an initial concentration of HF of 0.10 molar, and I want to know what is the pH of this. I'm going to assume that I'm starting with 0 of these because it hasn't disassociated yet. So this looks an awful lot like an ice table scenario, which it is. So I'm going to go down by some amount. So my equilibrium concentration of HF is going to be what I started with minus what disassociated. So now I'm not reacting, I'm disassociating. I'm going to have this is going to go up by the same amount, and this is going to go up by the same amount. So when I write my law of mass action, it's going to look like this. I'm going to have Ka, because this is acid disassociation, H3O plus F minus over HF, and remember I can exclude water from this because that's not going to affect anything. So now I can just plug my values in. So Ka equals X times X over 0.10 minus X. And I could solve for X if I knew Ka, and I know Ka because I have this table and I can look up these values. So you can always look up your acid disassociation constants. HF is here at 6.8 times 10 to the minus 4. So I can plug that in here and I can solve for X. So now I want to know, can I use my X is small approximation? Because it would be really nice if I could remove this using my X is small. Can I do it? I'm going to look at my concentration, my initial concentration, my equilibrium constant here, my acid disassociation constant, and if they're more than 10 to the third apart, then I can probably do that. So if I put this into scientific notation, this would be 1.0 times 10 to the minus 1. This goes to 10 to the minus 4, so that's right on that cusp. So I'm going to say yes, and I'm going to remove this, and I'm going to calculate. So I'm going to remove that X, which is going to keep me from having to do a quadratic equation. So see how much easier that math is? And then when I take the square root of that, that's going to give me an X of 8.246 times 10 to the minus 3. So that's my X. That's how much things have gone down. Let's check that assumption. So let's do check our X is small assumption. So I'm going to take my value of X, and I'm going to divide it by my initial concentration. That's going to give me my X is small approximation. So this is 8.2%. So this is greater than 5%, so that means that I can't use my X is small approximation here. And it was iffy because I was right on that cusp. So if this is greater than 5%, then I cannot do this shortcut. And I'm going to have to go back in and solve for X using the quadratic equation. Like I said, we'll do a lot of these calculations when we come together for our Zoom meeting. So percent ionization. This is the extent of dissociation. So the greater the Ka, the more dissociation, more ionization. The smaller the Ka, the less dissociation, and that's going to be less. And the way that we're going to calculate this is we're going to take the ratio of ionized acid to the initial concentration. So we're going to look at H3O plus at equilibrium over HA initial times 100%. And that's going to give me my percent ionization. So I'm going to find my hydronium ion concentration equilibrium because this is directly what's dissociating here. And then I'm going to divide it by my initial concentration and multiply by 100. If you're thinking that sounds a lot like the X is small approximation assumption, check, it is. So we did the same thing up here with this. And so this told me that I can't use my X is small approximation. So I need to come back in and I'm going to solve for X, and X is going to be a different value here than this. It's probably going to be something less than that. But I can also take that, then my new X, divide it by 0.1, and that's going to give me my percent dissociation. All right, and we will do some of those calculations when we come together in our Zoom meeting. So the one last thing I want to cover is what happens when I have a polyprotic or a mixture of acids, and I want to calculate the pH. If I have a strong acid plus a weak acid, so my mixture is I have a strong acid and I have a weak acid, then I can ignore the weak acid and use the initial concentration of the strong acid to find pH. If I have a weak plus a weak, so this is the easiest one because I can basically ignore what's happening here because this is going to have so small of H3O plus contribution that is negligible. So I can ignore it. But if I have a weak plus a weak acid, a mixture of a weak acid plus a weak acid, now I can't ignore the weak acid because the pH is coming from the weak acid. So what I can do is I can ignore the weaker acid of the two and calculate pH based on the initial concentration of the stronger of the two acids. And the way I'm going to know that the stronger one is it's going to have the larger Ka. So I'm going to compare Kas. So here I'm going to compare Ka values. And I'm going to calculate the pH based on the larger Ka value. All right, so that's where I want to end. We'll start part 3 talking about bases, and then we're going to switch and look at what's happening in ionic compounds and apply these principles there.